Hi, and thank you for watching. Welcome to my channel. My name is Dana. This week's topic is transformers in large language models. So for this week's video, I used 3 Blue, 1 Brown's video on transformers and how LLMs work, as well as Code Basics video on transformers. So we're all familiar with ChatGPT, and the GPT portion of it stands for Generative Pre-trained Transformer. ChatGPT actually does run on transformers, and a lot of modern AI uses transformers to help predict data and learn how to do things that we want it to do. And now the G we said is generative. It basically makes the new stuff. P is using data learned or still to be learned with the training data that was provided to the machine. And the T part is the transformer. This is the core of the network, and as well as the core of modern AI. And different types of transformers used to generate content. There's either a voice to text or a text to voice. You can write something to the AI and it'll create an audio out of it, and vice versa. So voice to text, I guess the most common little example I could think of is Siri. (3B) 1B uses a high-level view of the model to kind of answer the how question, and he takes things from a very high-level preview. So the text is basically created using a prediction model, which uses probability and statistics to kind of guess what the next word should be. And specifically, it uses a probability distribution to see what word is most likely to be next or not. So the cycle of predicting and sampling the model goes through that over and over and over again. I don't know, maybe millions of billions of times. And that's kind of how it quote unquote learns how to write. And let's take, for example, ChatGPT 2 versus ChatGPT 3. GPT 3 has a much larger number of parameters of which it can take in. So its prediction and the sample that it generates is a lot better than ChatGPT 2 because it has more options for the following token to pick from, as opposed to the second GPT. So the more data that there is for the model to work with, the higher the probability of the machine will generate a more reasonable or more meaningful response to the user. So tokens are a big part of embedding. Now, tokens are little pieces of data that are broken up, which we'll get a visual for in the next couple of slides, from the input given to the machine by the user, whether it be images, data, sound, text, whatever it is. And then these tokens are kind of placed into vector spaces. Like if you could imagine a 3-dimensional realm of an XYZ coordinate or an XYZ plane. So these vectors hold something meaningful behind the data that is inside of them, and we'll go through that later on. But there's a meaning behind the vector, and it's a big web of relationships that correspond to each other. And then vectors then go through something called an attention block, And this is where they talk to each other and they give each other attention, essentially. So that way, using that relationship that they compare with each other, they kind of know where to snuggle in and where they belong versus where they don't. And there's also something called the multi-layer perception, which is where vectors lie. And here they're parallel, so they don't ever really touch or interact. And this is where you kind of ask the vector a whole bunch of questions to evaluate its values and give it relative values compared to everything else. And basically it's just a big pile of matrices waiting to be multiplied. Well, for the multi-layer perception, I guess something that it reminded me of when police officers in TV shows and movies, they isolate people that they want to interview as opposed to leaving them in the same room, so that way their information, so they can't corroborate and swap information and make sure their stories are straight. So I feel like that's what the multi-layer perception is from my perspective. Hopefully that's accurate. Okay, so our tokens, this is an example from 3B1B's video. He kind of breaks down the tokens in a visual kind of array, I guess, and the question marks are what is the following word that should come out of the sentence using the LLM. And you can kind of do that, create that same idea with images and audio. Now the cycle that determines what should come next happens over and over and over and over and over again. And it goes from the attention block through the multi-layer perceptron. And that is how the learning is done, essentially. Now, the vectors give us significance behind the words. I'm sorry, it doesn't give it to us, it gives it to the machine. So if we take the dot product of two vectors, well, we know that if the dot product is 0, those are perpendicular. If they're both positive, they're obviously both pointing in the same direction. And then if they're negative, we know that the two vectors are in opposite directions. So there's a lot of tools that are used to compare relationships to one another. And we'll get a visual on that later on, and that'll make a little bit more sense. And if the vectors also tend to be a little closer to each other, or like they're almost on top of each other, then that means that they have similar meanings. So that is another tool to help us help the machine learn. And matrices have a whole bunch of words and texts, and again, we're using relative relationships to compare things, and softmax actually helps turn random numbers into some kind of meaningful distribution for the model to learn. And now here's a visual for embedding. For example, if we have king and queen, what is the authority that a king has? What is the authority that a queen has? Does it have a tail? No, they both don't have tails. They're both rich, and their genders aren't the same actually, so we have kind of a negative relationship to those two. And here, if we take a look at the 3D vector space, we're kind of doing a directional comparison to the king and the queen versus an aunt and an uncle. They're obviously opposite genders, so they're going to be pointing in different directions. Now, a good way to think about the attention block is like, what two words do you constantly hear that are always paired together? Well, a quick Google search helped me find some examples. For example, salt and pepper, peanut butter and jelly, knife and fork. Some of them are not likely to be together. I don't know where those came from, but I think that goes to show maybe that's why LLMs are not perfect, because it's difficult to predict what words will always be together, because that's not always possible, as we know, because we speak literally English. So it's difficult to always 100% guess what's going to come next. So for the attention block, Code Basics had a really good parallel that helped me understand it a little more clearly. So for example, let's say you're looking for a book in the library. So the query of the attention block is the name of that book you're looking for. What is the book you're looking for? The key is kind of the little details that help you find the book. So where is the rack? What's the description of the book? And the index number, like the little serial numbers that the books have. And now the value is the content on the pages inside of the book. So those are the little breakdowns of what the attention block holds for us. And thank you for watching my video.